Thank you so much. I'm here today to share with you something I'm quite passionate about. If we can go to the first picture to give you a sense of that. This astronaut is in orbit. They're moving at about 17,000 miles per hour, or about 28,000 kilometers per hour. But that astronaut feels like they're floating. They don't feel like they're moving at that rate. And the reason that they feel like they're floating is because the motion of that free fall is actually canceling out. That's the process of being in orbit. And from the motion of that free fall, it cancels out the force of gravity pulling that astronaut down. And so the perception, the perceived force environment that that astronaut is in is one where there is no gravity. Sometimes you'll hear people talk about that as zero gravity or microgravity because there's a little bit of force in there. And it provides for scientists an absolutely fundamental opportunity to do experiments that we can't do anywhere else on Earth. Because on Earth, we always have the gravitational force. There's some folks that have come up with something clever that maybe gets away from it for a few seconds here or there. But the only way to take advantage of this free fall and to do an experiment where gravity is controlled as an experimental factor is by going into orbit to do it. Now, I want to give you a sense in some very down-to-earth ways of what it means when you go into gravity and don't have those forces, or basically go into orbit and don't have gravitational forces in the way. Here you see a bottle of salad dressing. One of the first things you notice when you go into space is there's no sedimentation. So little spices in your bottle of salad dressing aren't going to settle out. In fact, the oil and water may not unmix in the same rate that they do here on Earth because the gravitational force isn't pulling on it. Also, you don't have buoyancy-driven convection in space. Now, buoyancy-driven convection sounds like a bunch of scientific jargon. This is the easy way to illustrate buoyancy-driven convection because that is something that is warm rising, warm gas in a hot air balloon rising, something that's cold falling. That's an example of buoyancy-driven convection. That doesn't happen in space either. And so what I want to take you through today is how these fundamental physical pieces can affect every system, from a physics experiment to a life science experiment to the human body itself, and show you how this laboratory provides an opportunity to take advantage of all of that to do some of the most innovative science that I think we'll see in the coming century. This is a little diagram to illustrate what convection means in a fluid. Think of this as a pot of water that you're boiling for some spaghetti, and you can see that the water molecules inside there, because of the buoyancy-driven convection, are rising and the cold molecules are falling, and you get mixing in that liquid. And I want to show you what happens when you do that same kind of a boiling a pot of spaghetti experiment in space. And so here on the left, you see the 1G example, and on the right, you see the space example. What basically happens is that on Earth, of course, as you know from boiling water, the bubbles just gradually form on the bottom of the pot, and then they rise up. In space, what you get is dramatic bulk boiling, where first you have nothing, 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 and then all of a sudden, in a flash, a large amount of the water boils all at once, and you suddenly get a large gas bubble right in the middle, and that bubble never rises. Then a few other bubbles on the side will eventually coalesce with that giant gas bubble in the middle. What you see there then is the process of that transfer, that energy transfer that happens when you boil, all by itself without convection in the way. And that kind of a fundamental change of being able to look at something without gravity messing it up allows you to learn things about physical systems that you can't learn here on Earth. In the same way that I talked to my 8-year-old daughter about how to do a science experiment and controlling each piece of that, in that same way, if we don't control gravity, there are certain physical systems that we will never understand perfectly, and that's what makes having an orbital laboratory so important. Here's another example for you of how dramatic convection can be. On the left is a candle flame burning down here on Earth, very familiar to you. On the right-hand side is a candle flame burning in orbit. And what you see there is because the warm gases are not rising away from that and cooling as they flow away, you get this very spherical form of combustion. In essence, you're seeing combustion in a more pure form without gravity forces getting in the way and the convection getting in the way. So this year, we finished assembly on the International Space Station, and scientists now have, from now until 2020, with any luck, maybe 2028, so certainly maybe beyond 2020, to use this laboratory. In the history of human spaceflight, we've really only had weeks of opportunity across the whole 50 years of human spaceflight. We've only had a few weeks in orbit to do different experiments. Sometimes scientists would do an experiment, they had to do it in a day, their next opportunity would be 6 years later. Now on the space station, we have 24/7, 365 laboratory access, and we have a space station now that the assembly is complete that's being operated to do all of these experiments, to do the experiments that control gravity. And so I want to show you, every picture I show you from here on out comes from the space station, and I just want to share some of the best gee whiz examples of what that laboratory means and how scientists get surprised when we take gravity away and we don't expect what's going to happen. And so I'm going to show you some examples just from this year on the space station. What basically happens is that the flame, you have a combustion event. There's a little droplet of fuel, that's a droplet of heptane on there, and then by induction, the combustion occurs, you get a glow, just like you would expect, or like you saw in the blue candle flame, and then the combustion event snuffs itself out as the products of the combustion surround it, prevent the oxygen from getting to the burn, and then it all goes out. Then there's a pause. And then just a couple seconds later, there's suddenly a really large afterglow where all of the combustion products that have dispersed throughout the container that it's in all glow. And it's only happened with a couple of the fuels we've tried. Nobody expected it. Scientists are working on what in the heck has happened. And this is an example of those eureka discovery moments. Now, we don't even know the explanation for this yet completely, and scientists have something to work on before we'll know. And even the combustion scientists that have been burning things in space for 20 years had no idea this was going to happen. Completely took everyone by surprise. And of course, combustion, this is theoretical, but combustion is really important. And the more you understand about combustion, the more you can make things like energy-efficient engines. And those are things that could really address problems that face our society. Another example of an experiment that I'd like to show you that really surprised people on the ground this year. This is an experiment that lots of fifth graders do in their science classes. You can see there's a balloon there, some static electricity has been put on the balloon. If you drip the water slowly enough, the static electricity will attract the water, and you can see that nice bend in the stream coming out of a faucet there. Well, some fifth graders from California proposed to do this same experiment on the space station, and their proposal was rated as one of the best proposals of the year in our Kids in Microgravity competition. And so Katie Coleman, who you just heard from, and her colleagues on orbit completed the experiment. So I'd like to show you. First, they're taking a piece of exercise tubing and rubbing it with a cloth to put some static electricity on it, getting it nice and staticky. And now we'll pause a second, and then we'll come back and see what happened when they took a drop of water out of the drink bag and released it near the tubing. And there it goes. So look what happened. That little droplet is orbiting the tubing. Now, nobody expected that. Everybody expected it to just get drawn into the tubing and stick, right? But instead, it went into orbit around the tubing. Experienced engineers, the guys who have worked on fluids and worked on engineering in space for years, sat in the control center and went, "What was that? What happened?" It's amazing. And this is just a simple experiment that fifth graders thought to try in space. And so we continue to discover that our instincts about physical processes are so captured by gravity and our experience here on Earth that when we go into space, we can make some amazing discoveries. Now, this moves from the physical realm to the biological realm, and I can't tell you all of the details, but let me just give you a couple of highlights. Scientists are using the fact that microbes, bacteria, become more able to cause disease when they're in orbit, and there are some interesting reasons they think that may be, but because of that, we've got 2 teams developing vaccines against salmonella food poisoning using the International Space Station as a laboratory. Cells divide in different ways in space. These are yeast cells that have divided not in the same plane. So you see all the scars there from each cell division that the yeast has done. Scientists are using that to study wound healing and to study differentiation of cells and see if they can find better ways to control that. This is a crystal that was grown by some of our Japanese colleagues that is an important protein in the pathway for Duchenne's muscular dystrophy. That's a disease that affects about 1 in 3,000 boys. It's a genetic disease, and they are now testing in models a potential drug to help reduce the effects of this debilitating disease, and that's using the physical processes of space to get a better quality crystal. And one recent discovery from this year, even after 50 years of human spaceflight, we keep learning things about the astronauts themselves. We've discovered that up to 60% of our long-duration astronauts have vision problems that come from being in space. Experts are still trying to evaluate why that is, and that may even be another window into understanding both the optic nerve and the fluid system in the human body. Now, you may have heard during the assembly of the space station, there were a couple of vocal scientific communities that said they didn't really want the space station. And if you looked at their credentials, a lot of those guys happened to be astronomers. Because astronomers don't really study physical processes in this way. They want to look out. And so what I want to share with you is why astronomers are finding the space station really valuable as my last example. And here you see an artist's rendition of a recent discovery made with data from the International Space Station from the MAXI instrument, combined with data from the SWIFT satellite. This is an event, it was published in Nature in August of this year. This was an event where a black hole swallowed a star, and that created a relativistic jet that shot out on each side that was seen as X-rays here on Earth. That happened billions of years ago, but that sign or those X-ray signals got to Earth just now. The instrument on the International Space Station saw it 2 hours earlier than the NASA instrument on a free-flying satellite, and the scientists put the data together to get the best possible instruments of the power in this event. And of course, now we have the alpha magnetic spectrometer looking at the very nature of dark matter, and they've collected over 7 billion observations of galactic cosmic rays. So we're really excited about what the space station means for physics and discovery in the physical realm as well. I've gone through a wide variety of disciplines really quickly. But what I'm really trying to communicate with you is why I, as a scientist, stepped away from my own research and have gone towards managing this laboratory to ensure that it's available and optimized for as many different scientific disciplines as possible. It's a powerful laboratory. The discovery potential is amazing. And because the space station has been declared a national laboratory by Congress, that means you don't have to come to NASA for money to use it. Any scientist anywhere in the country can come on board. Pharmaceutical companies are using ISS. University researchers are coming straight to the space station with research that they've developed. Even school children are raising money to go in some of the very inexpensive facilities that we've developed. So it's really accessible, just like any laboratory on Earth. And I'm so excited about the things that scientists are going to do in the coming decade. Thank you very much.